In this video, we'll discuss amplitude and period of sinusoidal functions. In particular, we'll define the amplitude and period and look at how to determine it given either the equation or the graph of a sinusoidal function. We'll find the amplitude and period given a formula, and we'll determine the formula given its graph by using the amplitude and period that we see. A sinusoidal function is a function whose graph has the same basic shape as a sine or cosine curve. The graph will consist of a wave, which could have a different height or a different period as the sine and cosine function, but will have that same general wave shape that the sine and cosine functions share. The general form of an equation for a sinusoidal function would be y equals a sine bx minus c plus d, or y equals a cosine bx minus c plus d, depending on whether the function is a sine or a cosine curve. And in these general forms, the numbers, or the letters a, b, c, and d all represent real numbers. What we're going to do in this video is look at what the numbers a, b, c, and d represent in terms of the functions and also in terms of the graphs of those functions. We'll start with simplified versions of these equation forms by letting c and d equal 0, and we'll be left with y equals a sine bx and a cosine bx. So our first goal is to determine how the values of a and b affect both the function and its properties as well as its graph. Two of the basic properties for sine and cosine curves are their amplitude and period. By amplitude, we mean the vertical distance between the maximum y value of the graph and the midline of the graph. And by the period, we mean the smallest horizontal distance on which the graph repeats. At the bottom of the screen, we have the graph of y equals sine of x. We've already seen that this has a period of 2 pi units. If we look, for example, from x equals 0 to x equals 2 pi on this graph, if we were able to reproduce this red portion over and over again, we would get the entire sine of x graph. Because this is the shortest distance on which the graph repeats, we see that we do indeed have a period of 2 pi units. And this is the smallest length on the x-axis where this will repeat, and because it's the smallest distance, that gives us our period. For the amplitude here, we really need to start by identifying the midline of our graph, and in this case, that is the x-axis. If we kind of sketch the x-axis in green, notice that this cuts horizontally right through the middle of our graph. The graph goes 1 unit above and 1 unit below, indicating this is the middle of our graph. And the amplitude here, we're told, is the vertical distance between the max value, which here is 1, and the midline, which is 0. And so our amplitude is equal to 1 for the graph sine of x. Both of these numbers are also true for the cosine graph. We will not show it, but we do know already that the cosine graph has a period of 2 pi. If we take the part between x equals 0 and x equals 2 pi, it will repeat to produce the entire graph. And the cosine graph also bounces between -1 and 1, meaning the midline is the x-axis and the maximum height of the vertical distance there between the max height and the x-axis will be 1, just like it is for this graph. When we have a more general sinusoidal curve, the values of the numbers a and b in the formula will actually give us the amplitude and period of that sinusoidal function. Let's start by analyzing the role of the number a, which is the number out front of the sine or cosine function in our sinusoidal curve. At the top of the screen, we have 4 sinusoidal curves, all involving the sine function, and the value of a is 1, 2, 3, and 4, respectively. We can see that the blue function is f of x equals 1 sine x, which is our normal sine function, and it has an amplitude of 1. The midline is, as it is for all of these functions, at the x-axis, and the function goes up to a height of 1. So the amplitude of this function would be 1. The second curve, the more yellowish-orange curve, f of x equals 2 sine x. Again, the midline is the x-axis, and the height of the wave is 2 units. It goes up to x equals 2. And so the amplitude of our second function there is 2. The third function, the green one, f of x equals 3 sine x. Again, midline is the x-axis and a height of 3. So this has an amplitude of 3. And lastly, we have our red function, f of x equals 4 sine x, which has a midline of the x-axis and goes up to 4 and its y values. And so it has an amplitude of 4. And so the pattern here is hopefully very clear, that the number in front of our sine function will determine the value of our amplitude. And so in particular, what we can conclude from this is that the amplitude of either y equals a sine of bx or y equals a cosine of bx, we didn't actually show anything for cosine here, but the same properties would apply, is the absolute value of the number a. The absolute value, of course, doesn't play a role in the examples shown here, but because it's possible for the number a to be negative and the amplitude is a distance, we always want to have a positive amplitude. And so in order to ensure that, we want to define the amplitude to be the absolute value of the number a in front of our sine or cosine function. We'll next look at the role of the number b to determine how that affects the graph of the curve. We'll start here by noting that the orangish function is f of x equals sine x, our standard sine function. And here we have a value of b equals 1 and a period of 2 pi. Again, we knew this was 2 pi because we know what the graph of the sine function looks like and that it repeats every 2 pi units. If we look at the dark blue curve, which is f of x equals sine of 2x, we see that we do have a b value of 2 because it's sine of 2x. We also see that this graph has a period of pi units. After we go from 0 to pi on the x-axis, we've hit the entire curve of our graph. It goes up to the max value, back down to the min, and back to the midline. And that part of the graph would then be repeated over and over. And so our period for this function is simply pi. So it's not quite as simple as just indicating the number b, but we will see a pattern here shortly. For the third function, our green function, we have a b value of 1/2. X over 2 can be rewritten as 1/2 times x, so that b is equal to 2. And we don't get an entire period here of our graph. We see that we go up to hit the max value and then back down to our midline at 2 pi. But there is another half of our period. The graph is then going to continue, and this, of course, is definitely not to scale, but it continues over something like this. And when it hits over here, this will actually be another 2 pi units of the dotted graph. So this will actually go out to 4 pi before it completes a full period. And so our period here for the function where b is 1/2 is 4 pi units. Right now we have 3 examples here of the period and the value of b. And though it might not be clear immediately, once we write it down, we should be able to verify, at least for these 3, that this will be true. The period is calculated by taking 2 pi, the period for the sine function, and dividing it by the number b. Right? So when we substitute b equals 1 into this formula, we just get 2 pi, which is the period of our standard sine function. When we substitute 2 in for b, we get 2 pi divided by 2, which is just pi. And if we substitute in 1/2, we get 2 pi divided by 1/2, or 2 pi times 2, which is 4 pi. And so this formula for the period does work in the 3 graphs we've seen here and works in general for both sine and cosine curves. So again, this applies to cosine curves even though that's not depicted here in our picture. So the period of a sinusoidal function is determined by the constant b and given by the formula 2 pi divided by b. In this example, we want to find the amplitude and period of the function y equals negative 5 sine of 4 pi x, as well as graph 1 period of the function. So in order to do this, we first need to identify the values of a and b in our sinusoidal curve formula. Here a will be the number negative 5, and b is the number 4 pi. And once we know this, we can use our formulas to find the amplitude and period of our function. The amplitude, we know, is the absolute value of the number a. So in this case, the absolute value of negative 5, which is 5. Notice that the absolute value here was important. If we simply said the amplitude would be negative 5, that wouldn't make sense because the amplitude is a distance, and a distance of negative 5 doesn't mean anything. We will see when we graph this function how the negative plays a role, because it is important that there's a negative there, just not for the amplitude. For the period, we want to take 2 pi divided by the number b, and here the number b is 4 pi, so we have 2 pi divided by 4 pi. The pi's will cancel, leaving 2/4, or better known as 1/2. And so our period of this function is 1/2. Now to graph 1 period of our function, we're going to use the amplitude and period that we just found. So we know that our amplitude is 5, and so we know our graph is going to have a height of 5, so it's going to go up to y equal 5. And similarly, it's going to go down to negative 5. That'll be its min value. And we know the period will be 1/2, and so over here I'm just going to label 1/2. This will be our ending point for our graph. All right, now, we have to remember that there is a negative value in front of our function. We have this negative 5. So what we're going to do is start by ignoring the negative. So I'm going to start by just graphing the function y equals 5 sine 4 pi x. Now notice the amplitude and period of this graph are exactly the same as the of the function that we're trying to graph. So here we have a sine function, and we know that the sine, when we do the period, we know the sine is going to start at its midline, which is the x-axis, and it will end at the x-axis. Normally, the sine will go up to its max value, return to the midline, go down to its min value, and then go back to the midline. Again, this is not the graph we want. This is y of 5 sine 4 pi x with the positive in front. So this is what this graph would look like, and this is how we would use the amplitude and period to produce a period of the graph. We would know that in this case, we have a sine function, so we're going to start at 0 on the y-axis, go up to the max, down to the min, and back to the x-axis. Now we have to pay attention to the negative sign. So what the graph that we really want is y equals negative 5 sine of 4 pi x. A negative in front of a function like this simply reflects all values across the x-axis. It takes any positive y value and makes them negative with the same magnitude, and any negative y value and makes them positive with the same magnitude. And so here I simply need to reflect this red graph across the x-axis. This means the graph is going to first go down, hit its minimum value, return to the x-axis, go up to hit its max value, and then return again to the x-axis. And so the blue graph here is the graph that we were looking for. But we obtained it by starting with the red graph and reflecting it across the x-axis. If you're comfortable enough with these types of graphs, you could jump straight to the y1 by drawing the reflection without having drawn the red one. It's always important to keep in mind that when we have a negative value for a, we are going to do a reflection of the graph and not the graph itself. If you'd like to practice with a similar problem, try to find the amplitude and period of the function y equals 3 cosine of 1/2 x, and to graph 1 period of this function. The answers in the graph will appear in just a few seconds. Notice that for the graph here, we want to graph a period of the cosine function, which will begin at its max value, in this case of 3, go down, hit its min value, and then go back to its max value. Because the value of a here is positive 3, we're going to draw an actual cosine graph like this and not a reflected value. In this example, we want to do the reverse of the previous example and find a formula for the given graph. So when we look at this graph, the first thing that we notice is that the graph starts at its maximum value and does not in particular start at the midline of 0. And so just by looking at that starting point, we know that we have a graph of a cosine curve. So we're going to be looking for a formula of the form y equal a cosine bx. Again, we know it's not a sine curve because a sine curve would start at the origin. And so we're looking for cosine curve, and we need to find the values of a and b. So when we look at this graph, we notice that our amplitude, the distance from the max value to the midline, is going to be 6. And we see that the period of our graph is from 0 to pi over 4, which is pi over 4. And so from this, we can reverse engineer the values of a and b. We know that the absolute value of a is equal to 6, the absolute value of a being the amplitude, and therefore we know that a is equal to plus or minus 6, the only two values whose absolute value is 6. In this case, our graph is not a reflection of the cosine graph. It is just a standard cosine graph starting at the max value. And so because it's not a reflection, we're going to pick a equal to positive 6. We also know the period here is pi over 4. And we know that the period is equal to 2 pi over the number b. And so we can solve this equation for b. We can solve this a couple different ways. For example, if we do cross multiplication, we see that pi times b will equal to 4 times 2 pi, or 8 pi. And then dividing both sides by pi, we get b is equal to 8. And so we put all of this together, and we see that the equation or the formula for this graph will be y equals 6 cosine of 8x. And this is the graph, or this is the function or the formula that would produce the graph shown here. If you'd like to practice with a similar problem, try to find the formula for the graph shown here. The formula and all of the attributes will be shown in just a few seconds. So note that this is a sine curve because the period of the graph begins at the origin and not at its max or min value. We get an amplitude of 2 from the graph, and therefore we know a is plus or minus 2. And in this case, we actually know that it is negative 2 because this graph is the reflection of the standard period of sine. The standard period of sine initially increases to its max value before then going to the min value. Since this is the opposite of that, the value of a will be negative 2. The period here is given to be 16, and so we can use 16 equals 2 pi over b and solve for b to find b to be pi over 8, giving us the formula y equals negative 2 sine of pi over 8x.